So this is GATE 2019 question number 40, which states that the vector potential inside a long solenoid with n turns per unit length and carrying current I written in cylindrical coordinates is, the magnetic vector potential is given as S phi z. We will see what is S phi z because it is in the cylindrical coordinate. It is given like that, mu naught ni by 2 S phi cap. If the term mu naught ni by 2 S in brackets alpha cos phi phi cap plus beta sin phi S cap, where alpha is not equal to 0, beta is not equal to 0, is added to this A, which is given here, the magnetic field remains the same. If, what is the condition of alpha and beta, or what is the relationship between alpha and beta, for which the A, the magnetic vector potential A, which is given like this, and A plus this particular term, which is given here, they will contribute to a magnetic field which are same. We have to see this. So for that, the solution will be like this. So this is the 40th question's solution. It is given in the question that the magnetic vector potential in the cylindrical coordinate system is phi z, that is A is equal to mu naught ni by 2 S phi cap. So what is this S phi cap? So actually this is for a solenoid. So solenoid looks like this. So we can approximate this to a cylindrical or a cylinder kind of a coordinate system, which is easy for us. So in the question also it is given in the cylindrical coordinate. So what is that? This is your z, this is x, y suppose, and this is how the cylindrical coordinate looks like. I'm just showing the some particular section of the cylinder where this is your S, whatever notation is written here. So this is S, the radial distance. This is your phi. This is the phi, the tangential angle, and this is Z. Or the unit vectors are S cap, phi cap, and Z cap or K cap, whatever we can write. So this is the unit vector, and they are all mutually perpendicular to each other, as you can see it here. Fine. Now given that, it is given in the question that if we add an extra term in the magnetic vector potential A, which is given here, if we add some extra term, say that term is T, that is mu naught ni by 2 S alpha, this is a bracket, alpha cos phi phi cap plus beta sin phi S cap. So this is the extra term which is given in the question, and it has been said in the question that if we add this extra term T to this magnetic vector potential A, we get a new magnetic vector potential A dash, that is A plus T. Now the magnetic field B for the vector potential A is same as for that of A dash. This is given in the question. Therefore, now what is to be found out? To find that if the above condition, that is, if B of A is equal to B of A dash, that is the magnetic field due to this A vector which is given, and the magnetic field due to the A dash after adding this term T is same, then what will be the relationship between alpha and beta is what we require to find. Okay. So for that, we simply know that B is equal to del cross A. From where it is coming, B is equal to del cross A. We know that Maxwell's second equation, if we talk about Maxwell's second equation, if we see the Maxwell's second equation, what is that? The divergence of the B, the magnetic field, is 0. Now, divergence of a magnetic field is 0, fine. But we also know that the divergence of curl of some quantity S is also 0. Divergence of a curl is 0. Therefore, or some, let us write it A. Therefore, this B can be written as del cross A. So B is actually del cross A, and this A is actually defined as the magnetic vector potential, because it's a vector. Why? Because there is a curl sign here. So curl of a vector quantity, curl cannot be of a scalar quantity. Therefore, A is a vector potential, and since it is related to the magnetic field, it is called the magnetic vector potential. This is the core theory. Now for the vector potential A, we have BA is equal to del cross A, the curl of A. Now how to find out this del cross A in the cylindrical coordinate system? So this is in cylindrical coordinate system. We write curl as this, or you can directly use the formula which is there in the question. So it's better to write it like this. Del cross A can be written as 1 by S 1 by the scale factor, and scale factor for cylindrical coordinate is r, or the radial distance. So scale factor for cylindrical coordinate system, cylindrical system, is s, the radial distance. This we need to remember. Actually it is 1 comma s comma 1. So if you multiply all those, it comes out to be s. So 1 by s has to be written like this, and this is the formula of the curl, if you remember the mathematical physics concept of this particular thing. Fine. So this we can write s cap, s phi cap, the scale factor has to be multiplied with each of these unit vectors. So 1 into s cap, s into phi cap, and k cap. Delta delta s, delta delta phi, delta delta z, the three variables in the cylindrical coordinate system. And corresponding to s cap, there is nothing in the magnetic vector potential, because A is only in the phi cap direction. So we have written it in the phi cap direction, but we have to multiply with another s. Why? Because here also in the third row and in the first row, these scale factors are multiplied with respective unit vectors and respective magnitudes. So therefore here 1 into s cap is multiplied, here s into phi cap, and there is 1 into k cap. Similarly 1 into 0, s into mu naught ni by 2 into s, which is the magnetic vector potential, and 1 into 0 again. Now if we do this curl, we get only in the k cap term, as you can see, will be the only thing which is remaining, and we get the magnetic field due to this vector potential A is mu naught ni k cap. And we know that for a solenoid with n turns per unit length, we get mu naught ni as the magnetic field vector, and that is also in the direction of k cap. Fine. So this is valid. Now A dash is when we add some extra term. So from A, if we if we add the extra term t, which I have written here, if I add this term, we get this as the A dash, the new vector potential. So this is this is now not only at phi cap, but it is also in the s cap direction. So it has a component in s cap as well as phi cap, unlike the earlier one where it is only at phi cap. Now the new magnetic field due to this vector potential, new vector potential A dash, is del cross A dash. That is also same 1 by s, and the same way it is done. Again you can see that this s is multiplied with this particular term, because you have to remember that the scale factors are 1 s comma 1. So this individually has to be multiplied. So do this curl, and ultimately we get B of this A dash comes out to be like this. Several calculations, just simple solving this determinant, and finally we get this is the result: 1 by s mu naught ni s plus mu naught ni s alpha cos phi minus mu naught ni by 2 beta s cos phi. This is what we get. Now it is already given in the question that the magnetic field due to A and due to A dash will be same. So we just write this is mu naught ni, we have already found out due to this, and due to this we have got this expression. Just chop this s in all the terms, you can chop this s, and finally you get this result. So mu naught ni can be cancelled out, only these two terms remain, and I take this particular term on the left hand side, and we get this minus mu naught ni alpha cos phi, that is equal to minus mu naught ni by 2 beta cos phi. You cancel each and everything, mu naught ni cos phi, mu naught ni cos phi, so we get alpha is equal to beta by 2. And this should be the relationship between alpha and beta in order to satisfy this particular relationship, that is the magnetic field due to the vector potential A should be equal to the magnetic field due to the new vector potential A dash when an extra term is added. So D must be the correct option for this particular question. So if you come back to this particular question again, you can see that alpha is equal to beta by 2 is the correct option given in this particular question. So D here is the right answer. Thank you.